In this video I'm going to look at gas chromatography, or GC for short. Gas chromatography is used to separate and identify volatile compounds in a mixture. And by volatile we mean substances with low boiling points. So if I just talk through this diagram on the board, and then we'll focus on this area here and talk about how the separation actually takes place. So we've got a mixture of various compounds with low boiling points, and they would be injected at this point here. And the mobile phase, so the substance that moves in this separation technique, is the carrier gas. So the carrier gas, the job of that is to move the components in the mixture through this very, very long, very, very thin, almost piece of wire. It's actually hollow, called a capillary column. And that can be anywhere up to 30 meters long. And it needs to be that long to make sure that the full separation actually takes place. So if you imagine you've got your mixture, remember these are substances with low boiling points. As soon as they get into this oven, they're going to evaporate, and the carrier gas is streaming through, and it's carrying these substances through this column. They will separate out because they're going to interact with the stationary phase, so that's the walls of the capillary column. I'll talk a bit more about this in detail in a moment. They're going to separate out as they travel through, and they will hit the detector at different times. In a nutshell, if a substance hardly interacts with the stationary phase at all, it's going to hit the detector very quickly. If a substance interacts with the stationary phase quite a lot, it's going to slow it down, and it's going to hit the detector after a longer period of time. That would then be sent to the computer, and a chart or a graph would be produced. So we'll look at the mode of separation now. You'll notice I've drawn a bigger version of the capillary tube now. So the black shaded area just represents the sort of walls of the tube, their solid support, and the purple represents the stationary phase. That's the phase obviously that doesn't move. Now in this case I've said that the stationary phase is a solid. So if we imagine we've just injected our mixture of volatile substances A, B and C. So at the very, very start they're all mixed together, they're all at the same position if you like. The carrier gas, that's the mobile phase, is going to carry these substances through this capillary column 30 meters. And I didn't mention before, the carrier gas would be something like nitrogen or helium, so an inert gas. It's not going to interact with anything, and the substances as they travel through will start to separate. So if the stationary phase is a solid, the mode of separation would be by adsorption. So these three components in our mixture are going to interact with the stationary phase by different amounts. And if you look at where I've positioned A, B and C now, A is sort of lagging behind, C is in the middle, and B is flying through. So the carrier gases really find it quite easy to send that through the capillary column. So what does that mean in terms of the relative adsorption? Well, obviously A must be interacting quite strongly with this stationary phase. So this is adsorbing quite strongly with the stationary phase, which means the carrier gas is struggling to take it through. C is adsorbing the next strongly, and B is probably not really adsorbing at all with the stationary phase, and so the carrier gas can send it through quite easily. So remember what happens once they've gone through the capillary column, they hit the detector. So obviously B is going to hit the detector first, and so that's going to have a short retention time. So that's what we measure when we operate gas chromatography. The time it takes from the injection of the sample to the detection of the component is what we call the retention time. And so B, because of its weak adsorption, will have a short retention time. A would have the longest retention time. So the retention time there, you can see I've written, it's the time from the injection of the sample of the mixture to the detection of the component. Remember, these are separated out by the relative adsorptions. So time from injection to detection. And then once the retention times have been measured, the analytical chemist would then go to a database and look up the retention time and compare it with the data value from known substances, and would be able to identify the substance from that information. So I've changed the stationary phase now from a solid to a liquid, and you can see that the separation now is by relative solubility. Retention time still the same, time from injection to detection. So again, we're going to inject the sample. So again, I've just got A, B and C. The carrier gas, this inert carrier gas, is going to carry these components through this 30-metre capillary column. They are going to interact with the stationary phase. Some are going to interact more than others, and the ones that interact the most will be slowed down. The ones that interact the least will fly through and have a short retention time. So I'm going to get you to think now. I've changed A, B and C into some actual named molecules. So we've got methanol in green, we've got ethane 1,2-diol in red, and we've got pentane in orange. And you'll notice I'm saying now that the stationary phase is a liquid alkane, so something with a very high boiling point which won't evaporate in the oven. And I've added a little phrase to help you work out how the separation is going to pan out. Like dissolves like. So pause the video and see if you can position the three compounds into the approximate positions according to their retention times. So to help us explain how the separation takes place now, I'm going to use this phrase, like dissolves like, and we're going to think which of these three is going to dissolve the most readily in the stationary phase, and it's obviously going to be the one that's most like it. It's the alkane. And that's because this alkane can form van der Waals forces with the stationary phase. And that's obviously going to slow it down. The carrier gas is going to struggle to move it through because it's dissolving into here. Now, since the remaining two molecules are alcohols, these form hydrogen bonds, which is kind of the opposite mechanism of dissolving to van der Waals forces. And so therefore, surely the one that can form the most hydrogen bonds is going to interact the least with this stationary phase, and so ethane 1,2-diol with its two hydroxyl groups is that molecule, and so this will travel through the most readily. And then just as before, we would measure the retention time, compare to data values, and that would help us to confirm the presence of the compounds, or if we didn't know what they were in the first place, we'd be able to identify what they actually were. The spectra look something like this, and so you can see we've got a retention time x-axis, and this one I've drawn out in minutes, and so you would look at the retention time for each individual peak and compare to data values for known substances. You'll notice also that the peaks have different areas. So this peak here has got a much larger area than these two. That's a bit bigger than those two. And the relative peak area tells you the relative amounts of each of the substances. So we've obviously got lots of this compound here, and we've not got very much of this one here. We'll just finish with some of the limitations of gas chromatography now. So you can see I've written up there, many chemicals have the same retention time, and so therefore you wouldn't be able to tell them apart. You could have a group of chemicals that are very similar in structure, and therefore they would have similar retention times. They wouldn't really separate out, and you may have one peak hiding under another. And the final one, if you're dealing with a completely new substance, it may have never had its retention time measured, and so you don't have a reference peak to compare to. So because of these limitations, gas chromatography is often used alongside mass spec, and the purpose of the gas chromatography would be to separate out the components in the mixture, not really to identify them. Once they've been separated out, their mass spec would be analysed, and mass spec can measure MR values very, very accurately, and you would be able to identify a substance from its mass spectrum.